Great. Well, good morning, everybody. Nice meeting you all. Sorry we're doing this virtually, but I see a few people in the room, a few people joining online, so I think we have a good mix. My name is Rocio. I'm the founder of a small company that is located here in Tampa, Florida. Our company is SkyTel, and we have a software platform for reduction of natural disaster risk. So one of our goals is to take publicly available information and data sources in scientific models and tools that are developed in academia, in research, in government labs, and look at how can we make them operationally so that they can run timely and effectively and inform decision making for emergency responders on the field. So one of our first use cases, we've been working on this for the past 5 years, is a wildfire management tool. And it's the wildfire management tool is called Wintel. So today, I'll talk just a tiny little bit about what we're doing with Wintel. And then we took a lot of, as I said, a lot of the research tools that we found publicly available, some that we developed as part of our PhDs, master's thesis, and we try to see how we could make them operationally so they can inform firefighter decisions on the ground as they are fighting the fire and maybe not post operationally. So I'll talk a little bit about how some of the lessons learned, some of the things that were successes, some of the challenges we encountered, and then hopefully we can put those in common and learn a little bit about everybody's successes, challenges, and opportunities, and how they've managed to turn not only Earth data, but also the scientific models developed by academia, in the research environment for operational perspectives, and what opportunities do we have to advance those models. So today's main goal is what we like to call, at least internally in our team, is collaboration for action. We like to think about, okay, we have a ton of data available. How do I make this information that a firefighter or even a community can act on? So if I have satellite information, if I have information from sensors, from drones, what do I need so that all this data it's converted into something, an insight that informs a decision in a very timely manner. So it informs a firefighter decision on, should I call for more resources? Where should I deploy my engine? Where should I send the firefighter? What are the most dangerous places? Where do I use the evacuation zone? So those are the kind of questions that we're saying, okay, we have all this data. What are the types of models? What are the types of tools? And how can we have them run fast enough and accurately enough so that they can actually inform those types of decisions? And how do I present it to the user in a way that it's going to allow them to make that decision rather than maybe overwhelm them with too much information? So here for the researchers in the room, I consider myself more of a researcher. I started the company and I had no background in business whatsoever, but I'm a little bit of a geek on data science and especially natural disaster science and earth science. So hopefully we can put in common among the researchers on the room, how can these data sets, models, and tools integrate and work together and produce something operationally? For emergency managers, I would love to hear if there are any in the room, what are those types of decision-making points and how can data help and inform those decision-making points when there is really very little time to make a decision, and what is the best way to present it? And then for those technologies, how can we work together so that maybe we all develop things? I think when we talk about natural disasters, especially, I think it's unrealistic to think that one person is gonna, or one tool is gonna solve it all. I don't think there is one single solution. So, but I think there is a lot of value on linking solutions so that they can run off of each other with only the human intervention that is needed. So how can we collaborate and join our efforts and our tools into something that can really serve those people on the field? So maybe a little bit show of hands. I think it's a little bit hard to do it when we are remote, but who here considers themselves a researcher? Me, myself, one. Okay, emergency managers. Okay, hi. Well, awesome. We can get some input from those in the field that can tell us, yeah, you're not doing this right, or this is what we need. So love to hear insights. And then technologies. Okay, so we have a mix of both. That's a really really insightful when we have operational field personnel who also are savvy on technology. It's invaluable information. So, okay, let's get into it. Again, what are we discussing today? I'm going to share a little bit of what we discussed. Dave, I see that your hand is on. I don't know if it's still on from the technologist or you're trying to ask a question. Okay, great. Okay, so when we're in our perspective, there were three main areas that we focused when we started talking to those on the field that maybe had the opportunity to use some tools but were or not were using them. And as we valued their feedback and we gathered their feedback, and also we gathered the feedback of the technologies, we looked at three main areas and we said, okay, if we want to take some of these fire spread models, some of these tools that are informing fire risk in where fire is going to propagate and help make decisions on the field, what do we need to solve from a technical perspective? So from our earnings and learns, we found three main areas. One, it was we need better data. If we're going to model fire spread of satellites that are only coming every 12 hours, by the time we get the next prediction, it's really hard to provide an hour by hour without the right real-time data inputs. So we need to have a way of integrating more data inputs into the models that have already been developed and the equations and the physics. So how do we gather those inputs? How do we standardize them? How do we normalize them? And how do we validate them so that they can act as inputs for these physics models? The second part that we heard is some of these, especially when we're talking about fire propagation, they take so long to run. I can't afford running a model and have it run in 20 minutes, in hours in a supercomputer because it's not going to inform anything on the field. So how can we use emerging technologies like cloud, acceleration using machine learning so that we can approximate some of these models and give results sub-minutes or even sub-seconds that can actually be used? And then the third part is we're being overwhelmed by information. We cannot have a user interface, or we cannot have 10 user interfaces when we're having this type of models and discussions. So how do we design a user interface that is user-centered, that is super easy to use? One of the issues that we found is that, for example, fire behavior models, and maybe I'm preaching to the choir if there are some emergency responders, they are only being run by fire behavior analysts because they need to be very specialized and trained, and they have to do calibration while the fire is running, and they have to modify the inputs so that it actually represents what they want. So if we're not able to produce something that requires less manual inputs and less calibration, it can't be used by at a scale, or it can be used by those in the field. And then the last part that we really heard was there is more and more and more technology coming out, and everybody's having their own user interface. And we cannot deal with 10 user interfaces or 5 user interfaces and 5 different tools. So as technologists, how can we collaborate so that maybe we share our data so the person in the field only needs to use one application and it's what they're used to and that's what they're trained on? So those are the three areas that at least we've learned a lot and we worked on. We'd love to hear if anybody wants to share any other areas, but if not, I will dig more into these three areas, and hopefully we can share some lessons learned and some opportunities and challenges and collaborate on these topics. Yeah, Dave, I see your hand.
Hi, thanks. Yeah, I just had a quick question on like just what are the challenges involved with trying to integrate or just use research models for operational decisions because you don't really know what's in those research models to have them behave a certain way when you're trying to maybe make decisions or understand things better. That research to operations transition is always a tricky one.
Yeah, that's a big part of our research. I think from our perspective, I would say that first it was direct collaboration with the researchers and then also with those on the field. And then the second part, it's back to integration of real-time data or near real-time data that can validate. So as you're saying, sometimes you have to modify these research models to give them the right inputs so that they can produce and simulate what you're seeing on the field. So we saw that if we are able to ingest data from the field to validate our models or calibrate them, then we can help a little bit modify those inputs for the next run. So let me give you an example. When we were doing fire forecasting and fire propagation, we were seeing that our model predicted the next 2 hours or 3 hours or next hour of fire spread. But then the next satellite that we were using from NASA VRs, it didn't come until the next 12 hours. So there is no autonomous calibration that we could do on that. It would have to be us and the firefighter on the field saying, no, I also see the fire spreading this way, or it's actually spreading faster than what the model is saying. I'll talk about this use case, but we started integrating aerial mapping data from aircraft that were flying over the fires. So now we have the next hour ground truth. So now we can start to autonomously calibrate some of these models and say, okay, you predicted this was the rate of spread, but I'm actually seeing that it's spreading faster, or that the conditions have changed, or the vegetation has changed in this way, so we can do some autonomous calibration. So it's a really long process. It's very complex, but at least that's one of the ways that we found to overcome some of those challenges.
Great, thanks.
But yeah, let's dig a little bit into each of these, and then we can all share some of the ways that we've overcome this and the challenges that we've encountered. So let me introduce our fire risk management platform. It's called Wintel. And as I mentioned, we're trying to take cutting edge fire science and make it operational in the field. And we saw that the models that were out that maybe were being used or only being used to document decisions rather than actually inform timely decisions, they were using static predictions that were not adapting to these changing conditions, that it didn't really integrate many data from the field in real time. And then the last part was they were taking so long to run that sometimes it wasn't useful, or it wasn't being able to be used during the operation rather than just maybe again for documenting decisions. So Wintel integrates data from satellites, drone sensors, responder inputs, and it does this dynamic modeling where it kind of calibrates itself, and it integrates and say, okay, I'm starting to grab data from the weather service on forecast data, but now my wind sensor is giving me a point measure. So let me recalibrate my wind estimation. So it does that type of dynamic modeling, and it takes everything into a hybrid cloud processing tool that can link the weather forecasting with a wind solver, with a fire spread, with an Embercast. And it doesn't need to be run, all of them, they don't need to run separately. They're automatically linked and they use that data in the field. So that's what we had the big vision with Wintel. And at the end of the day, our goal was we need to output information that can be used to make decisions. First, because it's accurate. Second, because it doesn't require a huge workload on the operator that is running it. And third, because it can be run in a timely manner. So if it plays, I just show a little bit of the interface. This is a use case from the Palisades that I put because I think everybody has heard of the use cases. So I'll stop talking for a little. So just a little bit on Wintel, and so that you can get an idea of the platform. Sorry, I think I need to come back. Okay, so there are some wildfire models that maybe if anybody is familiar also with wildfire science, are very widely known, like FlamUp, Farsight, Wind Ninja is a wind solver, and we combine some of the models that we developed as part of our own research, like an Embercast, or what we call WindPin, which is a physics-informed neural network to resolve the wind from different point measurements. Then we take the terrain into account and we resolve the three-dimensional winds. This was a way of, for example, Wind Ninja, that's a very similar effort, but it takes a little bit longer to run. So we use a neural network, a machine learning approximation to be able to run this a little bit faster and also be able to resolve winds in the three dimension. So I'll talk more about it, but just one of the examples of how we took some of the models that had been developed in research and said, okay, how can we do a machine learning approximation that is going to give us very similar results and run faster? So, and then we take the data sources, heat signatures from satellites or aircraft, drones, run them through computer vision models, and that gets fed into this computing engine where we house all of our atmospheric and fire behavior tools. The topography and vegetation, similarly, we grab it from some data sources like Wildfire that are open source and developed by the Forest Service, or we also use Sentinel data, for example, because it has a 2 to 3 day revisit time, and we apply computer vision to identify the type of vegetation. And then finally, the weather. We also use a combination of National Weather Service data with third-party data, and then also wind sensors on the field so that we can get refined winds. Mix everything together, goes into our atmospheric and fire behavior tools. Those tools are linked together so that they're shown as different types of layers in the user interface. The last thing we do is we connect with some of the platforms that we've heard firefighters use, like the Team Awareness Kit, if anybody's familiar with that. We heard some emergency responders, that's their preferred tool of choice. So instead of using our own user interface, we send the information there so they can visualize it wherever they need to, in the same application they're already using. And then same thing with other applications that emergency responders and communities. We're currently working on integration with Watch Duty, which is another application that is very widely used, and any other types of our technologies. We integrate via API, and that way we try to avoid overloading the end user with one another application that would be our own user interface. Okay, so as I spoke, we focused on these three key areas, and we looked at a iterative development process. So first, it was really discovering what those on the fields were struggling with, and really engaging in as many conversations as we could. And it's never enough, because you always keep hearing feedback and problems and perspectives, but that's a really big part of the design. And as we were talking earlier, with Dave's question, going from what the research had in mind when they developed the tool, how they developed, listening to them, and then also listening to the people on the field, so that we can translate the requirements into the design process. And then after that, really identifying, okay, so if I have to do this, if we want to operationalize this, what are the inputs that I need? What is the resolution from a temporal and spatial perspective of the data, so that I can produce outputs that are going to be useful? And once we had that, then it was all, let's go into the labs and start developing and coding and validating, and then evaluating. So we ran through a 3-year pilot program with emergency responders, with researchers, where we took the tool. At the beginning, it was many scripts on a local machine, ran them offline, and then identified what worked, what didn't work, so that we could refine the platform. And now it's just become this iterative process where we try to listen to the researchers, the end user, and continue to validate, evaluate, and iterate. So I'll go into the three main areas of today's session. First area would be real-time data integration. As I mentioned, in our case, we really want to make sure that we have fire data as fast as we can and as often as we can. So we start with satellite information that gives us hotspot signatures every 12 hours, and that's the NASA VIIRS. And then said, okay, every 12 hours, that's not enough. So how can we complement and enhance this information? So as I mentioned, there is a use case here from the fires last week. This was super exciting for us. One of our highlights. We were able to take the aerial mapping from an airplane in real time and produce fire forecast. So that requires a lot of integration and effort as well from our partner who's flying the airplane, who's sending the data. We learned a lot on latency. We learned a lot on coverage. They also have to deal with all the requirements involved with flying over the fire. But then once they're able to send it, Wintel automatically took those and refined, not only validated the prediction that we had done before with the satellite imagery, but we're also able to do a prediction of those fire perimeter maps. So super exciting there. We also use UAS imagery. So some of the emergency responders, they have drones, and they are starting, also commercial service providers, they're starting to map those fires. So we have a server where the drone video gets uploaded in real time, a computer vision model that maps the fires and the hotspots, and that gets integrated into Wintel. In this case, we've only done this on a prescribed barn in hotspot mapping, so we haven't taken drones to the fire just yet and demonstrated that on an active wildfire, but that's one of our next steps. We're working on that with NASA. And then field sense wind data and smoke sensors. those for us are very important to be able to accurately characterize the atmospherics that affect the fire propagation. So taking those into account as well. The use case is there, and what I would like to do next, what I was thinking about is, I know that there's researchers in the room, there are technologists, emergency responders, so maybe we can go into breakout rooms in the room, offline, or we can do it all here and talk about what are those data sources that are most useful, what are the data sources that are not yet integrated, but we see that with emerging technologies, it would be nice to be able to say, well, I have smoke sensors. We have Pano AI in California. Can we take their fire detections to start predicting where the fire is spreading? And also in other, it doesn't need to be wildfire. This is just the area that we've been working. My team has been working more, but maybe in your own use cases, what are some of those data sources that can really enhance the decision making and the models and the tools that are doing disaster prediction? And then what challenges we deal with latency, especially when it comes of aircraft, and when we have areas of remote areas where limited communication. So how do we overcome those challenges? One of the areas that I think as a technologist, as a researcher, has been incredibly important to work on is how to modularize and make all of these components on our tools modular so that they can talk to each other and they can ingest different types of data sources. And then what opportunities do you see to continue evolving these types of tools and making them better and making them more useful? So yeah, I would leave it to the organizers to decide what they think is better in terms of breaking out a virtual room, or maybe we can all talk here. Okay. I guess I'm not hearing anything, so we can all discuss on a single breakout or in a single room. Anybody would like to share any insights or answers to any of these questions? Or any comments?
We've got one.
We're passing a mic around the room so the online folks can hear as well.
Yeah.
Awesome. Thank you.
Sorry.
This is more of just a concern that came out of, as you were talking about Utah, Colorado fires. Recently, I'm from Utah, I'm the state hazard mitigation officer there. And with some of our firefighting and trying to get data as they're fighting the fire, there were drones that actually delayed fire, them being able to flying the planes to put out the fire. And so I just, as you're thinking about these data sources, a comment I wanted to make is to be very careful with those data, how you're going to gather data with something like a drone that may interfere with the actual firefighting. I probably have lots of other thoughts too. That was just something that just popped into my mind as you were talking about that. Another thing is that, yeah, we definitely are trying to find ways. We have our layers that we do for data from each of our counties or communities that will put in all of their infrastructure that's very critical. They all input that into a system. And then as we're trying to look at what's happening with the fire and what critical infrastructure is going to be threatened, being able to have a resource that would look at that actually faster would be really good on my side, and I'll leave my comment there.
Okay. Yeah, yeah, I would love to talk about that on the drone side. So I hear you. when on the Palisades, actually, we talked to the aerial firefighters, and they told us they had an average of 40 drone sightings per day, which is wild. My background is in drone integration, working as a contractor for the FAA and NASA. So one of the projects we have with NASA is on adding an airspace management tool to this. And it seems like it's completely unrelated to the fire spread, but we're not, like you're saying, we're not going to be able to integrate drones if we're not able to manage the operation safely. So it's a parallel avenue. We have not deployed any drones, and I fully agree with you. I think we need to be very, very careful about how we do those. So we know that it's possible from doing this on prescribed burns, but doing it on an active wildfire, it's very complex. So we're working with NASA on a separate project to develop the airspace management. But yeah, I think you're completely right. And sometimes it delays the mission, especially when it's unwanted drones, rather than actually providing any efficiency gains.
I had a related question to that. I admit not particularly fresh on drone regulations currently, but my understanding is that the FAA now has a rule that there's like a device in the drone that must be there, and it prevents the drone from flying in like particularly sensitive areas, think like military bases and that sort of thing. I wonder if is there a way that you could just, I don't know, totally stop hobbyists from interfering in the airspace above like an active wildfire?
Yeah, what you're talking about, yes, it's called remote ID. And
yes, thank you.
yeah, and what it does is that it makes the drone broadcast its position. So that's the technology we're using to at least show the emergency responder that the drone is there. For the unwanted ones, we have jumped the communication link, but that's been more for military purposes. If at least an emergency responder agency, or even me as the person who is providing the airspace management, I cannot jump that unless it's under a military purpose work. So you can technically, or at least, yeah, it's possible. We can't from a policy perspective. So all we're doing now is really just giving the heads up, giving the warning. You would be surprised how many people don't know they can't be there. So a lot of the times we provide the information or where the operator is and just give them a heads up. But I think there is a big part. So I think there is also a big part on education of like, hey, you cannot go and take pictures if there is a fire.
Yeah, and education is probably a better pathway than just making someone ground a drone. I could see, that eroding trust. Someone might be like, well, what are you hiding that you aren't letting me fly my camera up there?
Exactly, yeah.
I don't want to dominate the discussion if there's anyone else with comments.
There's definitely a growing drone usage during incidents, and there's been some really phenomenal development of thermal imaging, but it is not always, it is usually most effective during phases in which the incidents are kind of at a low risk phase, because the prioritization is always for the aircraft. It is definitely, there are more and more incident teams that are deploying with drone operators, and the aviation management is improving dramatically.
Yeah, are you in Canada by any chance, or you're in the States?
That's in the United States. Yeah.
Okay.
And, go ahead.
No. I'm just gonna say we met a very, very cool Canadian company who had a platform to aggregate drone data and georeference it, geospatialize it, and then distribute the layers. And they were using it in Canada very widely, like you're saying. And what they told us is mostly when the disaster or when the fire is being extinguished, to assess damage, to understand where the smoke is going, so that they were doing very great things.
There's a growing use of drone ignition mechanisms where they use it for burnout operations as a primary ignition mechanism, which is extremely popular. It is in accompanying that, the thermal imaging is growing in usage on drones. However, kind of calibrating the thermal imaging from those kinds of sensors is actually really tricky. It doesn't end up as, it's not easy, and certainly it tends to be that the UAVs, just for their data management practices, end up having much higher latency than the aerial assets for monitoring. Those are much more integrated into the incident decision support systems than the UAVs, and UAVs tend to be retrospective information, which is more, I'm going to say is to describe the context of an event more than it is to contribute to decision support.
Yeah. Our partner, I'm gonna give them a shout out to them, Trident Sensing, the ones that did the flying for us last week, or that they sent us the data. They developed a really cool sensor that is thermal imagery, and it calibrates very well. They have low latency, so they've been demonstrating it on drones under a NASA project on a research perspective, but they're getting really cool results. And at least when they are, it's very modular, so it can be put into the airplane or the drone. When they put it into the airplane, we found very good results. But I will agree with you that the hardest part was calibrating the intensity values.
Have you looked at the Pyrecast products that are being developed at this point for like live fire forecasting?
Yes, and we talk to them regularly. The way we see the collaboration is Wildfire in general, with Pyrecast being their main fire spread model. They are very good at managing the incident at large, in managing a lot of data with the supercomputers at UC San Diego. So this is a conversation that is in progress, because these types of tools, at least Wintel in our case, it's better used for that initial attack, where you need to have a very quick insight of where the fire is going, and we really focus on if it's a high wind event, where the embers are going to propagate, and whether or not it's going to be a very rapidly growing fire because of the embers. And then once that's done, I think Pyrecast and Wildfire in general does a much better job at aggregating huge amounts of data, aggregating data for all of the vehicles, drones, aircraft who are looking at the extended attack. So that's kind of how we see the two pieces working together. Okay, Dave, I see your hand.
Yeah, thanks. I'm just wondering how you, like the process that you go through when you gather data from the aircraft. I'm sure they don't have bandwidth on board to stream the video in real time. So I guess they land, they upload it to the cloud, and how much time elapses between the airplane gathering the data and when you actually get to a model result?
Yeah. So the cool thing with Trident Sensing is that they do their data processing on the airplane. So what they send to us is GeoTIFFs, and they require we don't get the video from Trident Sensing. We process video from drones, but for aircraft, for this use case in particular, or this integration, Trident Sensing processes the data. So they send us a GeoTIFF. So as they're flying, they get into areas where they have limited bandwidth, and they send that. And they're working on SATCOM integration. So we do get the data as the aircraft is flying, and we have an API integration. So we grab the data automatically. The data goes. They don't need to land. and upload the data. We don't need to grab the data manually. It's integrated via API. So everything happens, I would say these fires, we definitely had a forecast before they landed. I would say was 20 to 30 minutes, all into an hour. It depends on whether or not the area they were flying, they were getting some intermittent cellular connectivity. So they flew over the Deer Creek fire. We got results very quickly, and then the last fire they flew over was the Tornet Gulch, and for that one it took about an hour or two to get the results. But for the Deer Creek, it took 10 minutes, 20 minutes at most for us to produce the outputs.
Oh, that's great. So how accurate is the elevation data that you have?
Elevation data, we're taking that from Wildfire mostly. It's a 30-meter resolution. And then as far as accuracy, I can tell you, I could have my tech team give you better insight into what is the accuracy of the elevation. We also use what's called fast fuels. And fast fuels has LiDAR data. It's also used for a service application. It has LiDAR data, so it's incredibly accurate to the centimeter. And it's also 1 meter resolution. But fast fuels, for example, that takes much, much longer to run. So we only use that for smaller, like at the asset level or like critical installations, but we can't use fast fuels for mapping for fires all over Colorado and Utah, for example.
Right, right. So so that's great. Thanks for that. I'm wondering now about the weather inputs, the weather data. Are you using real-time observations around the fire? Are you able to access Forest Service weather sensors that they deploy around fires? Or are you using model output from like the HER model or something like that showing high-resolution weather forecasts?
Yeah, so our workflow works, starts with HER models. We pull the data from the National Weather Service. From the National Weather Service, we have Wind Ninja, which is developed by Los Alamos National Lab. It's a wind solver that takes topography into account and resolves the winds interpolates, if I can say like that, interpolates the winds using the topography information. So it will accelerate the winds over the ridges, for example. We also have deployed the wind physics-informed neural network. So we take into account the 3D and the terrain. And then if there is sensors on the field, we haven't integrated with the Forest Service. We don't have a collaboration with them, but we have a collaboration with other wind sensor providers. And right now we're developing our own just for testing purposes and to have some and it's based on commercial off the shelf. So when there is a wind sensor information, that comes in as a point measurement and it gets integrated into the workflow, combined or oversees what the Weather Service forecasted, and then goes into the wind solvers for the interpolation in between the points where we had true measurements.
Gotcha. Okay, that sounds great. Thank you.
Thanks for the question. Okay, I think we can go to the next topic. Thanks for the conversation. So the next topic for us was, how can we take some of these models and tools that were developed in academia, were developed in research, again, Wind Ninja by Los Alamos National Lab, Missoula Fire, Wind Ninja, it was Missoula, it's developed by the Missoula laboratory, and the FlamUp, Farsight are all other fire spread models. We developed our own Embercast model, and we also, as there were some comments on the back, bring critical infrastructure values. Okay, how can we take all of these tools and run them quicker? So we still have a ton of lessons to learn here, a ton of progress to make. but we had a few wins that I think in being able to accelerate these tools in these models. For us, the first part is, and I'll show it here, is taking physics models and using machine learning to approximate those results. So, for example, we had the Wind Ninja model that takes point measurements or forecasts from the National Weather Service, both of them, and says and interpolates that based on terrain. And it has two modules. You can run mass conservation, which runs fairly quickly, or a momentum conservation. If you want to run the momentum conservation, it becomes more of a CFD model. So now it takes much longer to run. So we said, okay, can we train a machine learning model to take the inputs, take the outputs, and approximate the results and try to run faster? So that's what we did. We developed what is called a physics-informed neural network, which means that at certain points in the simulation, the wind has to comply to a physics principle, in this case, the momentum conservation. And then everything else it learns how it should comply to that. So this is, for example, the animation. And Dave, this goes back to your question. Maybe we have data every 3 kilometers in here. So we're trying to interpolate how the wind behaves in 3 dimensions over in between those points. So those are some of the approaches for trying to replicate the field conditions as much as we can while keeping the time sensitiveness of the application. And then the second part, we have a nice partnership with Google Cloud, and they really helped us accelerate and deploy everything and all our tools, all the models, all the data workflows in a way that it's very, very efficient so that we can accelerate how the data flows from one model to the other and how the databases are implemented, developed, and then data is input and output from the databases so that things can run very quickly. So these are just some of the tools. We use Gemini to collect data from many historical fires over the years and extract parameters that can train our algorithms. We use Vertex AI to deploy machine learning models. The databases that we use is BigQuery, and then we use Google Kubernetes Engine. These are just some tools that have worked for us. I am not a cloud developer, so if there are any technical questions that go deep into these tools, I would have to refer to our tech team. But I think for our perspective, the new emerging cloud technology is giving us the opportunity to develop some tools and models that before had only been able to run in supercomputers. In doing some of those cloud accelerations, that really has enhanced our capability to take some of the tools in academia, some of the tools running in supercomputers or very big servers, and put them in a way that can be accessible in the field without having to connect via virtual machine or something like that to a computer on the field. So again, maybe we can go over this. If there are any comments, questions, what tools have worked for those technologies in the room to be able to deploy models in accelerate computation. What are the pros and cons of cloud? It can get very expensive. We know that, for example, running some of historical models of the cloud, that can get extremely expensive. What suggestions and what lessons learned does anybody have to find the right balance? And then what other emerging technologies, tools, and what are the challenges of accelerating or producing this in a timely manner? I think we had a comment early on about how can we get that information fast enough to the people on the field. So I would love to hear a little bit more insights into that. How do you understand what critical infrastructure is going to be affected much quicker? And so what are the challenges? What are some good time? Dave, you were talking about the latency between the airplane. What are some acceptable times? 1 hour, are we talking hours? Are we talking some minutes, sub-second when we deploy some of these tools? So just, I'll open it to the room if anybody has any comments.
One of the places in which technology adoption has been smoothest in the fire space is in the prescribed/beneficial fire space, where the identifying windows of opportunity for ignition is kind of one of the key decision points, whereas the incident infrastructure has a hard time adopting technology fast, or technologies that aren't like identified as their kind of core deliverables, because they are often under pressure in ways that make new data streams difficult to absorb.
Yeah, I didn't know much about the prescribed fire environment until about a year ago. We started working with the CERDEP at the DoD. Are you familiar with them? And the Forest Service with Brett Williams. So we're just working on integrating quick fire and fast fuels in Burn Pro 3D, which has been very fun. And as you're saying, I think it's great because it gives you the opportunity to test some of these technologies and some of these tools without having the time restrictions or requirements. And then once I think one of the great things is that we can take some of those lessons learned as we go into the incident management, where, of course, the scenario is so much more complex. I would love to pick your brain. We're actually submitted to a challenge in a couple of weeks by CEREP and the Forest Service. And how would you, they want to train using quickfire, and they're looking at what are those areas that we can identify the windows of opportunity, and what are the challenges today to identify the windows of opportunity?
Well, one of the strategies that is, shall we call it a hot topic right now, is burning adjacent to recent fire scars, because you have defined containment established by much larger features than potentially mechanically treated boundaries. So within existing recent fire envelopes, there are opportunities for much more aggressive burning than would be available elsewhere. So that is a large-scale strategy that is lots of people are kind of picking up on.
Thank you. Yeah, I didn't know that. That's a great insight. Okay, anybody else?
No other comments in the room? We'll see if there's anything online or in the chat.
Okay, so I'll pass it. This is the last topic that I was going to touch on today, unless, at least from the presentation perspective, happy to chat about others. But our last part was, there is an overload of information, and how can we take the information to the field in a way that can be acted on, that is not overloading the operator, that doesn't need autonomous calibration, that doesn't need constant calibration of the tools by those on the field. So I think for this, there is really no secret sauce other than trying to listen and iterate. So for example, I don't know if people here are familiar with the team awareness kit. We heard that some emergency responders were using the team awareness kit. So we were integrating via API and sending predictions through that user interface. That's one of the ways that we, from our perspective, we try to do it. I think I like to advocate always for open APIs and standard data exchanges so that when two companies are collaborating or we're collaborating with an end user, it can always be integrated with whatever platform is being used. So I think from my own perspective, that's an area that we have found a lot of success in working towards standardization, working towards open APIs in modules that can communicate with one another. And for those who may have, who are from private industry, I'll open the door for that collaboration. We love to work with other companies for validation, for integration. I think is the only way that we're going to solve or we're going to help is that if we all work together. So we always try to advocate for standardized data formats. And then the second part that was very interesting to work on and has been, and is a work in progress, is how do we link one model to another? And also, how do we calibrate the model? So if the model is doing something that is not entirely correct, can it get validation data in real time from measurements and use that to correct its prediction? So that's one of the key areas that we also try to work on. So for example, we forecast ember spread and ember ignitions. So whenever we have an ember landing or we project that embers will land, we have an ember probability of ignition calculation and algorithm that looks at all of the factors that can determine whether or not those embers are going to ignite a secondary fire. So temperature, wind, relative humidity, past precipitation, the state of the vegetation, what is the fuel type, and then give it a probability of ignition. So that, and what you can see in this figure, for example, is different colors. So the red would be a higher probability of ignition. The purple would be the lowest probability of ignition. And then the gaps that you see in between, that doesn't mean that so I should start with saying that these points, these color-coded points, those are the predicted ember ignitions, while the blue is how the fire may be propagating through the ground, and the red are the actual hotspots observed by the satellite. So, and wherever you don't see dots from the ember cast, that doesn't mean the model didn't predict an ember would be landing. It may have predicted the ember landed, but it said, well, maybe it's landing on water, or it's landing on an area that has previously been burned, or it's landing on a fuel that is not conductive to ignition. So it will remove those points where the probability of ignition is low. And that's a user-defined threshold. What is the probability of ignition that they want to see? So, for example, in that case, this model automatically calibrates its weights. So it can say, I'm doing probability of ignitions towards this area, but the embers are really not igniting. Why is that? Is it because am I not giving the right inputs in terms of what is the wind? What is the past precipitation? What is the current precipitation? Or is it because I'm weighting the winds and my weights on each of these factors today is not correct? So that's one of the examples that we're doing autonomous calibration of the model and using machine learning to learn what the model may not be doing correctly, and how can we, for the next prediction, the next time we are going to forecast embers from, if the fire is spread here, which is what we saw, why didn't it spread here? Is it because we're overshooting the embers because we're overshooting the wind, or we're overestimating the wind? And if so, the next time we can lower a little bit our wind value. So we're working hard on understanding how can we do some of that calibration that today fire behavior analysts are doing manually, so that we can reduce a little bit some of that workload. Oops. Okay, the image didn't load. It was one of these AI generated images, so nothing that adds a lot of value. So maybe we can go into discussion. what are the tools and methodologies to link the models, to link tools? How can we better, everybody, I think, but us first, integrate feedback from users in the development process? And what are the challenges with using some of these tools in operation for the decision making? I think we already had some discussion on what are the biggest opportunities to bring some emerging technologies into operations like prescribed burns, especially when it comes to drone operations where your airspace situation is not as complex. But what are other opportunities where we can save time for decision makers, where we can make decisions faster if we have the right tools? And also, what are those areas where we have a long way to go, or we need more research and more work? So I'll open it to the room for this last comment session. Thanks for keeping the conversation alive.
Okay, so there's one decision point that has been a regulatory point of friction that is, I think, a very big deal for the prescribed/beneficial fire community is getting to the point of decision with the regional regulators when there's a burn plan and a prescription. And one of the challenges is that there are these points in which you have people who are taking responsibility for large-scale risk. Essentially, when they're initiating fires, they are, kind of held to a pretty high standard, and there is managing risk at this point in which you're about to initiate a large prescribed fire is one of the trickiest places. But along the chain of kind of, I guess, responsibility, there are very different incentives and personas often case. So in some cases, you have perhaps like burn bosses who are committed to, they have raised a project up and have committed resources and are waiting for approval to start burning. I see that as being one of those places in which having models that can be shared between parties so that people are talking about the same facts on the ground could be very valuable.
Thank you. Thanks, I was taking notes. Okay. Thank you in the room for sharing the slides since I was having some technical difficulties. So if there are no more questions, we can go to the last few slides. Next, please.
Wait. Okay.
Yes.
Sorry.
No?
This one?
Yeah. So just a recap of the areas that we discussed today: integration of real time. How can we accelerate models and tools in human-centered design? One of the takeaways that I'm leaving with here is that that we can do a stepped approach. There are areas where integrating emerging technologies and technologies like this have a lower resistance, and we can take some of the lessons learned from maybe integrating this on prescribed burns, or as the fire is extinguishing, and we can use some of those drones, and then in areas where some of the challenges of these tools, like running in a timely manner, they are not as sensitive, like for example a prescriber. And then taking those lessons in looking at, okay, then how can we go to the more complex problem of maybe doing this on an active incident. So thank you for the conversation, and yeah, maybe we can go next slide, open it up for questions. My contact info is there if there are any more comments, but I think we also have a few minutes if there are any hanging comments, questions, concerns. or anybody who wants to share something that maybe we haven't touched on the presentation.
It's Friday. Everyone's a little tired. I think that's all
No worries.
happening.
I really appreciate the conversation. I'm sorry again for not being in person, but thank you for everybody who's contributed, everybody who spent their time here listening today. And yeah, happy to connect. Would love to keep hearing and keep the conversation up. And thanks for all the engagement.
Thank you so much for such a great presentation.